Okay. When we last left our excitement here, we did this problem where we did these mole ratios. So notice something the same about these questions that we did. In all cases, we gave a certain amount of reactant, and we calculated the amounts of either other reactants or products based on that. But what happens if you have multiple reactants and multiple amounts, and those amounts don't necessarily fit the mole ratio? Then you have a situation that's known as a limiting reactant situation. So this should be either limiting reactant or limited reaction. So let's go back up to our example that we just talked about. Not that one, that doesn't make any sense. Let's go up to this one. When we did this propane combustion, we said that 1 mole of C3H8 reacts with 5 moles of O2. And we said, okay, what happens if you have 2.18 moles of this? Then you'd need 10.9 moles of oxygen for it to react fully. But what happens if instead of 10.9 moles of oxygen, all you have is 8 moles of oxygen? Now this reaction is limited. The propane can't all react because there aren't enough moles of oxygen for it to react with. So there's going to be some leftover, and the oxygen is known as the limiting reactant because it limits the reaction. It limits how much propane reacts, and it limits how much of the products we can form. So I like to think about this with pizza. This is actually a picture from your book, but I think it works out well. And I'm hungry. So. Oh yeah, if you bring in pizza for the exam, you get 100%. Did you not? Really? Did I tell you that?
Sweet. Really?
No, not really, but you can pretend it's true and still bring pizza.
You should have said that.
I should have told you it was actually not true at the exam, but no. Yeah, just get a bunch of pizzas. Sorry. Anyway, all right. So this is how you make pizza, if anybody knows this. It has 3 parts. It has the crust, the sauce, and the cheese. If you're not familiar with pizza, that's the parts of it. So let's say that every pizza requires 1 crust, of course, 5 ounces of tomato sauce, and 2 cups of cheese. If you don't have that much of those things, you can't make a whole pizza. So if you have 4 crusts, how much tomato sauce do you need to make 4 pizzas? 20 ounces, right? And this, you notice how this is the same thing as that mole ratio? Yeah. And then how much cheese would you need for 4 crusts? 8 cups. Because 2 cups for each, and then there's 4 of them, so 8. So if you have 4 crusts, you can make 4 pizzas. If you have 10 cups of cheese, you can make 5 pizzas. If you have 15 ounces of tomato sauce, you can make 3 pizzas. Right? So what if you have all those things? That amount of crust, that amount of cheese, that amount of tomato sauce. We say that the tomato sauce is limiting because you only have enough tomato sauce for 3 pizzas. It doesn't matter that you have extra cheese and extra crusts. You can't make extra pizzas because you don't have enough tomato sauce. Now I'm really hungry, actually. So the other reagents, the crusts and the cheese, are in excess, and the tomato sauce is limiting because you need only certain amounts. Right? And it's the same thing with the reactions. If you don't have the exact molar ratio that you need, one of the reactants is always going to be limiting because there's not enough of it to use up all of the other one. So let's do a calculation where we're less hungry. Although I don't know, ammonia is pretty delicious too. Don't actually try to eat ammonia. That was a joke. Okay. If 3 nitrogen molecules and 9 hydrogen molecules are added to a reaction vessel, is there a stoichiometric mixture of reactants? Now, a stoichiometric mixture means that nothing is limiting anything. Everything is in perfect measure exactly as it should be. So the question is asking you, if you have 3 N2s and 9 H2s, is that stoichiometric or is one of them limiting? If you have, yeah, So if you have 3 of these and 9 of these, is this reaction limited by 1, or is it all good?
It's good. It's good.
It's good, because the mole ratio is 1 to 3. So if you have 1 molecule of nitrogen, you need 3 molecules of hydrogen. If you have 3 of nitrogen, you need 9 of nitrogen. So it's all good. All right, so why? Why is it stoichiometric? Because we need 3 molecules of H2. Whoops. H2 for each molecule of N2, and that works. 9 is 3 times 3. Okay, second one then. If we have 5 molecules of N2 and 9 molecules of H2, is that stoichiometric or is that limited? It's limited. And what's the limiting reagent? The hydrogen is limiting, because we've got enough nitrogen that we would need how much hydrogen? Yeah, if this were balanced properly, if this were stoichiometric, you would need 15 hydrogens, because you need 3 times as many hydrogens as nitrogens. Since we don't have 15, we only have 9, that's limiting. So let's look at those. This is just summarizing what we just talked about. So we need more H2. Do we actually have the... Yeah. So let's skip down to this next page here. So if this reaction were 5 to 9, you had 5 nitrogens to 9 hydrogens, this is what you would get. You would actually get 3 of these and 9 of these reacting to make 6, and then you'd have 2 extra nitrogens that didn't react, like the extra crusts that didn't get their sauce because there wasn't enough sauce to go around. So now it gets a little bit trickier, and we have to use some of the skills that we just talked about before the break, which nobody remembers probably, but we'll try it again. So now if I say you have 25 kilograms of nitrogen and 5 kilograms of hydrogen, and they're reacted, which one's limiting? Now that's less clear, right? Because the limiting thing goes molecule to molecule. You need 3 molecules of hydrogen for 1 of nitrogen. It doesn't say anything about grams, so how do we figure this out? We have to convert it to moles. All right, so let's do that. 25 kilograms of nitrogen is how many moles? So we're going to multiply that by... Yeah, so first we have to convert to grams. I think we can do that without a fancy equation at this point. So that's 25,000 grams. And then we've got 17 grams per 1 mole. And how many moles is that? Oh, I was thinking ammonia. Sorry, yeah, you're right. I did ammonia. So what's that one? About a kilogram, or a little less than a kilogram? Okay, let's say 893 moles of N2. All right, and let's do the 5 kilograms of hydrogen. Should have some more space here. So that's 5,000 grams of hydrogen times 2 grams per, or divided by 2 grams per mole. That's 2,500 mole of hydrogen. Okay. So, which one is limiting? So to figure this out, you need to, the hydrogen is limiting. So you need to figure out how many moles of hydrogen would you need for 893 moles of nitrogen. You'd need 890, so we would need 893 times 3, which is 27 6 something, right? 26. So we need that many moles of hydrogen to fully react 893 moles of nitrogen. We don't have that. We only have 2,500. So that means that H2 is limiting. Okay. So now you go back to the equation here. There, 1, 3, 2. To answer this next part, what would be the mass of ammonia produced from this reaction? So if we know that hydrogen is limiting, which number of moles do we use to figure out the amount of ammonia that would be produced? So now we have to do this. Remember, we'll remind you of the reaction here. Whoops, that's not right. So it's 1 to 3 to 2. We're going to use one of these numbers, either 893, 2,500, or 2,679 to figure out how much ammonia we're going to make. Why 893? Why 2,500? That's the limiting one. So 893, if we use that, that means that all 893 moles of nitrogen react. But we know that's not actually the case because there isn't enough hydrogen for all of those to react. So we use how much hydrogen we have because that's what's limiting. That's the smallest one we've got. So let's do that. The ratio of hydrogen to ammonia, the molar ratio is 3 to 2. So for every 3 molecules of hydrogen, we make 2 molecules of ammonia, which means we're going to multiply 2,500 moles by 2 over 3. That's our ratio, right? Because 3 times 2 over 3 equals 2. Right? And that gets us about 160, what is it? So that's how many moles of ammonia is produced times (17 grams per mole of ammonia). So we'll say 28.2 kilograms of ammonia is produced. All right. And then finally, we could ask how much of the excess reagent is remaining. So which one is in excess again? Nitrogen was in excess. Do we know by how much? We can figure it out, right? How do we figure that out?
Subtract the starting amount by the amount that can react. That'll give you the amount left over.
But how do we know the amount that could react?
Because it's limited by the total.
Well, that's the number of moles of hydrogen that we would, extra moles of hydrogen that we would need.
Go back to the equation now.
So it's really, that's a way to get it, yeah. What are you gonna say?
Do we actually subtract 25 from 679? And the 179 we divided by 3 and then multiplied by the mole mass?
Yeah, that's one way you can do it. That's one way you can do it. The other way, which again gets you the same sort of thing, is to take the 3 and the 2400 and basically do this calculation in the opposite way. So say, okay, if we know that our 2500 moles of hydrogen is limiting, how much nitrogen does it react with? Well, the ratio, the mole ratio, is 1 to 3. So we would divide that by 3. Which is, whoops, not 0 point. About 800 something, right? Yeah. So that means that 833 moles of nitrogen were used, because that's how much reacts with the 2500 moles of hydrogen. So then 893 moles is what we started with, minus that 833 gives us 60 moles of nitrogen left over. That's the nitrogen that wasn't used. So this was kind of the big problem of this, where we asked every possible question. And this is why it's so important to do practice problems. The techniques are the same, but they can be asked in a few different ways. A limiting reactant problem can only be asked in a few different ways. I can ask which is limiting, which is in excess, how much in excess, how much of the products are formed, and how much is left over, which is the same as the excess. So this is kind of a rundown of how to do each of those different techniques. Let's look at a sample problem, and then we'll talk about a related thing, which is theoretical yield, which is just another way of asking the same question. So try this one together in your tables. Nitrogen gas can be prepared by putting it over copper oxide. All right. The other products of the reaction are solid, copper, and water vapor. So it's ammonia plus copper oxide gives you nitrogen gas, copper, and water vapor. What? If a sample containing 18.1 grams of ammonia is reacted with that much copper oxide, which is limiting, if any, and how many grams of the product will be formed? So you have to kind of go through and do all the stuff we just did. You need the equation, you need the molar ratios, so you need a balanced equation, and then you need to look at how much of the two reactants were used. Are they in that balance, or are they out of balance? And probably they'll be out of it because this is a limiting reactant problem. And by how much? So give that a try for about 15 minutes, if it takes you that long, and then we'll move on. All right. So nitrogen gas, we need the equation first. And I looked around, it looks like most people got that, which is great. Nitrogen gas is prepared, so it's not a reactant, it's a product, by passing gaseous ammonia over solid copper oxide. And the other products are solid copper and water vapor. All right. So to balance this, we need to balance the nitrogens and then the hydrogens, so 3 of those, right? And then 3 of these, 3 of those. Does that look good?
Yes.
All right. Sample contains 18.1 grams of ammonia and 90.4 grams of copper oxide. So what's the first thing we need to do? Find moles. So we're going to convert these two numbers to moles. 18.1 grams of ammonia is how many moles? And I was going to do it over here, but that's fine. 90.4 grams of copper oxide is how many moles? We'll put it over here, 1.14. Okay, so now we have moles. Now are those numbers in a 2 to 3 ratio? They're not. So what's limiting? The copper oxide. All right. If we have 1.06 moles of ammonia, we need 3/2 that, or 1.5 times that, copper oxide. So we need about 1.5 moles of copper oxide, and we don't have that. So that means that the copper oxide must be limiting. Now that we've identified that, how can we figure out how much nitrogen is formed? Do we use the limiting one or the one in excess? The limiting one, because that's what limits us. The excess isn't going to react. So that means that how many moles of N2 are we going to form? 1.14 divided by 3, because these are in a 3 to 1 ratio. So you need 3 of these to make 1 of these, and that's our limiting one. And what do you get there? 0.3 what? So 0.38 moles of nitrogen are going to be formed. And 0.38 moles of nitrogen times 28 grams per 1 mole gives you how many grams? 10.6 grams of nitrogen ultimately formed. Okay? So that was one example of what can be asked in these types of problems. If you go through the book problems, you'll see all the different kinds. You'll see how much of this is formed, how much is left over, how much is used, all of these kinds of things. It's the same type of calculation over and over again, just with a different number that comes out. Okay. One of the important, so this calculation isn't always this important, because when you're planning to do a reaction, you're going to choose amounts that put things in the proper ratio, or maybe put a little excess because you know it works well or something. But one of the reasons that you use this is to calculate something called theoretical yield. And you use that theoretical yield to get actual yield. And this is something that you do all the time for every chemical reaction that you perform in the lab, especially in fields like organic chemistry. You want to know how efficient the reaction was. So you have to take how much you start with, figure out how much you should get, and then compare that against how much you actually get. The how much you should get is the theoretical yield, and that's actually what we just did in this previous question. We found the theoretical yield of nitrogen. How much do we expect to get if everything goes perfectly? Which is not going to happen in the real world, because chemicals don't do that, but that would be theoretically how the reaction should go if every molecule of this reacted with every molecule of that in the proper ratio. So you get questions like this. 65 kilograms of carbon monoxide reacted with 8.6 kilograms hydrogen. Calculate the theoretical yield of methanol and then if this much methanol is actually produced, what is the percent yield? The percent yield is simply the actual yield divided by the theoretical yield in a percentage times 100%. So if they were the same, it would be 100%. All right, so to do a problem like this, you have to go through the same steps. You have to get the equation first. And the equation here is the manufacture of methanol from CO and H2. So you've got CO plus H2 yields CH3OH. And to balance that, all we have to do is say 2 hydrogens. Okay, there's our equation. Now we have 68.5 kilograms and 8.6 kilograms of hydrogen. Now we have to get these in moles, so we can either convert them to grams or just use kilomoles, which would be 1,000 moles. Same idea. What do you want to do? Convert to grams or use kilomoles? Okay. All right, so 68,500 grams then, right, of CO. Is how many moles? So you're going to multiply that by 28, or I'm sorry, divide it by 28. What is that? 2,446. All right, so 2,446 moles of CO. And then we've got the same calculation for hydrogen. And I'll just tell you that one. That one's 4,300 moles of hydrogen. So which one is limiting? The CO or the hydrogen? Well, let's look at it. If we wanted them to react perfectly, and we had 2,446 moles of carbon monoxide, how much hydrogen do we need? We need double that, right? Because it's 1 to 2. And double that is more than 4,300, right?
Right.
Okay, so hydrogen is limiting. It's limiting because we need 2,446 times 2, which is we got that? So we need 4892 to get all of the CO to react. And we don't have that, we have 4,300. So then how many moles of methanol can we make from 4,300 moles of hydrogen? Half of it. Yeah. So the 4,300 moles of hydrogen, which is limiting, makes 4,300 over 2, or 2,150 moles of methanol. Okay. So the theoretical yield then is this number, but in grams. This amount, I'm sorry, but in grams. So to get that in grams, we multiply that by the molecular weight of methanol, which is 32 grams per mole. And we get 6.88 times 10 to the 4th grams. And this is what we call the theoretical yield. That's the theoretical yield. That's how much we should make if we actually put these amounts together and everything goes exactly perfectly. Okay, then for the last part of the question, if this is the amount that's actually produced, what is our percent yield? So our percent yield is going to be the actual over the theoretical times 100%. So in this case, that's 3.57 times 10 to the 4th grams divided by 6.88 times 10 to the 4th grams, which is 51.9%. So we would report our percent yield as 51.9%. And if you look at any scientific papers where they do chemical reactions, they report a new reaction or something, they always report the percent yield. So you have a good sense of how much this makes. This is an important concept because if the percent yield is somewhat constant, you know how much you have to start with to get a given amount. So if we want to do this reaction and we want a certain amount of methanol, we need to pick our starting amounts not just based on the molar ratio, but also based on the percent yield, because we're only going to make about half of what we set out to make. All right? So you always have to keep those things in mind when you plan these reactions. Yeah?
Is that theoretical for the first grams?
Yes.
That number?
That is the molecular weight of methanol. So that's how we converted the methanol from moles back to grams. Okay, happy problem solving? Let me know if you have any, yeah. Yeah, sorry.